Hi everyone, this is Sai Teja from CSC AML section. Today my tech talk topic is about space imaging of a six-wave mixing in a Rydberg dressing atomic assembly. It is about the Rydberg dressing how he imaging of a six-wave mixing and how he did that equation into a atomic assembly. Now we are going to learn about it. Let's go into our topic. So in that, we are going to learn about the Rydberg atom and electron impact excitation, and also the charge exchange excitation, and also the optical excitation. And finally, lastly we are going to learn about the hydrogenic potential. Let's go into our topic. Introduction. Rydberg atoms are valency atoms that are excited to high-lying states with a principal quantum numbers. That is, we have indicated the principal quantum number n. We all know that n is greater than 30. It is a well known that Rydberg atoms have strong interactions and polarizability. We all know the Rydberg atoms have the strong interactions due to the octa-electrons in the outermost shell. Therefore, they sensitively react with the environment. Other atoms in the vicinity and the external fields. Based on these good properties, the larger polarizability of Rydberg gives coefficients under condition of electric field induced. The possibility of controlling strong range interactions has been demonstrated. In this, we are learning about the quantum numbers are highly excited due to the strong interactions and polarizability. And also an external fields based on these good properties, large polarizability of Rydberg gives coefficients under the condition of electric field induced. Let's going to learn about the Rydberg atoms, which has potential application in quantum information processing, a single photon observer and switching. Recently, a large number of induced nonlinearity has been found and investigated by the combining Rydberg's excitation because it can be provided group indexes as large to better reflected the normality response, especially many optical bistabilities which are caused by Rydberg's interaction. In this, Rydberg has a potential application in quantum information processing, single photon observer, and switching. Uh, Recently, a large number of amount of induced normality has been found and investigated by the combining Rydberg's excitation because it can be provide group indexes as large to better reflect the non-linearity response, especially many optic bistability which are caused by the Rydberg interaction. Rydberg atom. A Rydberg atom is an excitation atom with one or more electrons that have a high principal quantum number. It is denoted by n. The higher the value of n, the Rydberg atom is an excited atom with one or more electrons that have very high principal quantum numbers. The quantum number indicated by small n. The higher the value of n, further the electron is from the nucleus on the average. Rydberg atoms have a number of peculiar properties included and engage exaggerated response to electric and magnetic fields, long decay periods, and electron wave functions that approximate under some conditions, classical orbits of electrons about the nuclei. The Rydberg atom is an excited atom due to the more electrons having higher principal quantum numbers. The core electrons shield the outer electron from the electric field of the nucleus, such that from a distance, the electric potential looks identical to that experienced by the electron in a hydrogen atom. We can see the diagram which was shown on the screen, that image, how the electron orbital of a Rydberg atom with quantum principal quantum number n equal to 12 colors shown the quantum phase of the highly excited electrons. In this flowchart diagram, the 3D diagram of the hydrogen atom, the Rydberg atom with the number of electrons is 12, for quantum numbers is 12, with the colors quantum phase of the highly excited electrons, as we can see the picture. In spite of its shortcomings, the Bohr model of the atom is useful to explaining these properties. In this Rydberg atom of its shortcoming, the Bohr model of atom is useful in explaining these properties. Classically, an electron in a circular orbit of radius r and about a hydrogen nucleus of charge positive ions obeys Newton's second law. We can see the formula of Newton's second law, which obeys the hydrogen nuclei of positive charge, and the electrons are a circular orbit of radius r in a electron. We can see the Bohr model of atom is useful explaining these properties. In that F equal to MA, that is further derived into K of E square by R square, that is equal to M of E square by R, where K equal to 1 by 4 pi epsilon naught. This is the constant formula for the K value, and the R is the circular orbit of radius of an electron, and about a obeys the Newton's second law. Orbital momentum is quantized in units of x cross mvr equal to n h cross. Combining these two equations leads to Bohr's expression for the orbital radius in terms of the principal quantum numbers n. That orbital radius r equal to n square h cross square by k square of m. So this is the combining equation leads to Bohr's expression for the orbital radius in terms of quantum numbers. We can see the formula on the screen, and we can observe the Bohr's expression leads to two equations. It is now apparent why Rydberg atoms have such peculiar properties. The radius of the orbit scales as an N2. The N equal to 137 state of hydrogen has an atomic radius 1 mu 1 mu, and the geometric cross section as N4. Thus, Rydberg atoms are extremely large with loosely bonding valence electrons, easily perturbed or ionized by collisions or external fields. These Rydberg atoms have such peculiar properties. The radius of orbital scales as N2, that the N equal to 137 state of hydrogen as an atomic radius of 1 mu, easily penetrated or ionized by collisions or external fields. Because of the Rydberg atoms are extremely large with loosely bonded valence electrons. Electron impact excitation. Much early experimental work on Rydberg atoms relied on the use of collimated beams of fast electrons incident on ground state atoms. Inelastic scattering process can use the electron kinetic energy. Now we are learning about the electron impact excitation. How the electron impacting on the excitation. For that we must early experiment work on Rydberg atoms relied on the use of collimated beams of fast electrons incident on ground state atoms. Inelastic scattering process can use the electron kinetic energy to increase the atom's internal energy, exciting to the broad range of different states, including many high-lying Rydberg states. that E negative plus A tends to A of into plus E negative, electrons negative. Because the electron can retain any arbitrary amount of its kinetic energy. This process always results in a population with a broad spread of different energies. In this, the increasing the atom's energy, internal energy exciting to the broad range of different states. Many high-lying Rydberg states, charge exchange excitation. Another mainstay of early Rydberg atom experiments rely on charge exchange between a beam of ions and a population of neural atoms of another species, resulting in the formation of beam of highly excited atoms. A plus plus of B tends to A into plus of B plus, because the kinetic energy of the interaction can contribute to the final internal energies of the constituents. This technique populates a broad range of energy levels. In the charge exchange excitation, we are learning about the how the Rydberg atom experiment relies on exchanging charge exchanging between a beam of ions and a population of neutral atoms of another species. Because the kinetic energy of the interaction can contribute to the final internal energies of the constituents. This technique populates a broad range of energy levels. Optical excitation. The arrival of tunable dyne lasers in the 1970s allowed a much greater level of control over populations of excited atoms. In optical excitation, the incident photon is observed by the target atom, absolutely specified the final stage energy. We can see the optical excitation as a dye lasers in the 1970s allows a much greater level of control over population of excited atoms. The problem of producing single-state monoenergetic populations of Rydberg atoms thus becomes a some simpler problem of previously controlling the frequency of laser output. A plus gamma tends to A power cross. This form of directed optical excitation is generally limited to experiments with the alkyl metals because the ground state binding energy in another species is generally too high to accessible with most laser systems. In the problem of producing single state monoenergetic populations of Rydberg atom, controlling the frequency of laser output, which means by the Rydberg atom, it control simpler problem of precious controlling the frequency of laser output. Hydrogenic potential. An atom in a Rydberg state has a valency electron in a large orbit far from the ion core. In such an orbit, the outermost electron feels an almost hydrogenic Coulomb potential from a compact ion core consisting nucleus. A comparison of the potential in hydrogen atom with that in the Rydberg state of different atoms. We can see the graph diagram on the x-axis. We have taken the units from 1 centimeter to units, and y-axis we have taken negative as the 0.5 centimeter. We can see the how the radial distance was increasing through the going on to away from the potential, and it was how it was uh, going away from it, and it was changing the direction and also increasing its radial distance. An electron in a spherical symmetric Coulomb potential has the potential energy that UC equal to minus of E square by 4 pi epsilon naught into R. This is the spherical symmetric Coulomb potential formula. With the help of this formula, we can find the Coulomb potential for different atoms of electrons. The similarity of the effective potential seen by the outer electron to the hydrogen potential is defined characteristics of Rydberg states and explains why the electron wave functions approximate to classical orbits in the limit of corresponding principle. In this seen that outer electron to the hydrogen potential defined characteristics of Rydberg states and explain why the electron wave function approximate to classical orbits in limit of corresponding principle. Finally, images of Rybert swarm that evolve according to the power of the probe field are present to further investigating the spatial image characteristics of Rybert nonlinearity. In this, we have kept the three diagrams and we can observe how the changes was occurred by the Rybert according to the power of probe field. They are presented to further investigate the spatial image characteristics of Rybert normality. We can see the diagrams or graphs on the screen and observe the Rybert's kind of power of field. Thank you. In spite of its shortcomings, the Bohr model of atomics usefully in explaining these properties. Classically, an electron in circular orbit of radius r and about a hydrogen nucleus of charge was it obeys the Newton's second law. Orbital momentum is quantized in units of h cross. MVR equal to n of h cross. Combining these two equations leads to Bohr's expression to the orbital radius in terms of principal quantum numbers n. We can see the derivations of the principal quantum number of orbital radius. It is now apparent by Rybert atoms have such peculiar properties. The radius of orbit scales as M2 and the geometric cross-section as M4. The Rybert atoms are extremely large with loosely bounded valency electrons. The electron impact excitation work on Rybert atoms relied on the use of collimated beams of fast electrons incident on ground state atoms. Inelastic scattering process can use the electron kinetic energy to increase the atom's internal energy, exciting to a broad range of different states, including many highly Rybert states, because the electron can retain any arbitrary amount of its initial kinetic energy. This process always results in a population with a broad spread of different energies. Another of the early Rybert atom experiments relied on a change between beam of ions and a population of neutral atoms of another species, resulting in the formation of beam of highly excited atoms. The arrival of tunable dyne lasers in 1970s allowed a much greater level of control over population of excited atoms. In optical excitation, the incident photon is observed by the target atom, absolutely specified with the final stage energy. The problem of producing single-state monoenergetic population of Rybert atom becomes somewhat the form of direct optical excitation is generally limited to experiments with the alkali metals because the ground state binding energy is generally too high to accessible with more laser systems. You can see the hydrogenic potential on the graph and observe how it was formed. And we can see the distance, Coulomb potential and also radial distances. And we can see the Coulomb potential formula and similarity of affecting potential. You can see the electron wave function. Finally, images of Rybert that involved according to the power of the probe field that presented to further investigate the spatial image characters of Rydberg normality. Thank you all.